Hello, welcome to the last lesson of Unit 8, which is graphing log functions. We're going to start out with some review problems here. So the first thing we want to do is isolate the base with the exponent, rewrite in log form, and then solve with our calculator. Rewrite in the opposite form, I should say. So for the first one, we don't need to do any rewriting in terms of like a log or an exponent form. It's already in the exponent form, but because we have the same, or not the same exponents, but we have a base of 2, and we can take 32 and write that in a form of 2. We can break it up and think of this as 8 times 4, 2 times 2, 4 and 2, 2 and 2. We can rewrite 32 in a way that we would have the same base. Okay, so notice how we have 5 2's here. So that means that 2 to the 5th power is the same as 32. So now off to the side here, I'm just going to rewrite our problem. The first side's going to stay as 2 to the 4x. The other side we want to be 2 to the 5th power, but because we still have this x minus 1, we have to take that 5 and multiply it with the x minus 1. That's still a part of the exponent. So it's just like you're distributing. So we'd get 2 to the 4x equals 2 to the 5x minus 5. Now that we've written it with the same base of 2 and 2, we can go ahead and take the exponents, set those equal to each other. So 4x equals 5x minus 5. I'm going to subtract 5x from both sides. We end up with x equals, or negative x equals negative 5. Therefore, x equals 5 is our answer. Okay, this one here, we do want to try to isolate the part that has the exponent, which is this 5 to the power of x plus 2. So I'm going to subtract 3 from both sides. We get 5 to the x plus 2 equals 22. And at this point, we're kind of stuck because there's not a nice way to go from 5 to 22. We can't rewrite 22 with a base of 5 like we were able to on this one. So instead, what we want to do now is write in the opposite form, which would be the log form. So this is the log base 5 of 22 equals our x plus 2. The log equals the exponent. So I'm going to figure out what this is by typing it into my calculator using that change of base formula. We take the log of our big number here divided by the log of the base, which is 5. And then I also want to subtract 2 from that because I got to get rid of this. So whatever this whole expression is in the calculator, that's going to be our answer. Let me pull up my calculator here. All right, so log 22 divided by log of 5 minus 2, and then we end up with x equals negative 0.08 if we rounded 2 decimal places on that one. Okay, a couple more here to review. This one we're starting out in the log form. So we don't really have a way to get the variable by itself unless we rewrite it. So take your 4, bring it underneath the 2, and then you have 4 squared equals x plus 3. 4 squared is a nice number, it's just 16. So 16 equal to x plus 3. Subtract 3 from both sides, and we get a nice answer of 13. Remember to check when it comes to the log ones, because if you take the log of a negative number in your parenthesis part, that is going to result in a no solution. But in this case, 13 plus 3 would be 16, so we're perfectly fine there. Few more here. This one, if we have a number in front of the log, we should probably get rid of that immediately. So if I divide by 4, I'm left with log base 3 of 3x equals 20. Okay. This one here is kind of interesting because we do have log base 3 of 3, but x isn't our exponent. So we might want to consider this one a little bit differently. So here, what we can do is if we try to rewrite this one, This would be 3 to the 20th power equals 3x. I'm guessing that, oh, I forgot to divide by 5. That's why I'm like, this seems so big. I forgot to divide 20 by 4, which would give us 5. Now when we do it, it should be make a lot more sense. So 3 to the 5th equal to 3x. 3 to the 5th would be 3 times 3 times 3 times 3. So it ends up being 243. You can type that in your calculator. And then if we divide by 3, we get x equals 81, which makes a lot more sense. Okay, last one here. Remember that if your bases of the logs, which are 4 and 4, are equal, then you can set the pieces next to them, the x plus 3 and the 8x plus 17. We can set those equal to each other. So I'm going to move my 8x. We would get negative 7x plus 3 equals 17. Subtract 3 from both sides. We get negative 7x equals 14. Divide by negative 7. And this is where the issue ends up coming up, is we get negative 2. But if we take negative 2 and we plug it in, we just want to make sure that it works out. So if I do negative 2 plus 3, I do get a positive number. And then if I do negative 2 here, I would get negative 16 plus 17. So that does end up being positive 1. So it does work out. It's a good solution. So just be really careful with those negatives, because sometimes they do result in a no solution if it's the log of both sides. Okay, on to the new lesson for today, which is graphing log functions. And what we're going to do is we are going to rewrite them in the opposite form, and we're just going to graph them like we did with the exponential functions. They're just going to look slightly different. So here we would have our h and k. That's just what we subtract from it. And then the k value is going to move up or down, or subtract or add, excuse me. H is still the opposite, if we want to remember that from before. So this is still the opposite. But the h and k is going to serve as our shift point like it did for the other version. So if I have f of x equal to log base 3 of x, I want you guys to think of that as y equals log base 3 of x instead of the f of x. And then we can just rewrite this in the opposite form. So if we take the 3, this becomes 3 to the y equals x. And this is something that we graphed before. Now it's just like in the reverse order. This is the inverse of an exponential function. So we're going to make our x and y table. But because it's 3 to the y rather than 3 to the x, the numbers that we're going to put are going to be backwards. So before, when we were using the negative 2 through positive 2, we were putting it here. Now we're going to put it over here. Negative 2, negative 1, 0, 1, 2. And then the numbers that we were getting in the y column when we were graphing exponentials are now going to be over here. So it's like you're taking 3 to the negative 2 power, and that gives you the x value. And 3 to the negative 2 would be 1/9, because we'd flip the fraction and then square it. So we'd get 1/9. This one would be 1/3. This one would be 1. This would be 3. And this would be 9. So now when we graph these, and also I should have noted, but this is going to be at 0, 0. We don't have a new shift point because we don't have an h and a k value that we can see. So we assume it's at 0, 0. Let me just go ahead and add in our dashed lines then. So when we're graphing this, we want to make sure to think about the point 0, 0, because that's what we're going to be graphing from. But when you count this out, you have to be really careful, because now we're counting differently. We are counting the x value as our fraction, and then the y value is going up and down. So 1/9 negative 2 is just slightly over 1/9, and then down 2 is just a little bit in front of the y-axis. And then 1/3 negative 1 goes over 1/3 and down 1. So it's a little bit further away. 1, 0 is the point right here. 3, 1 goes over 3 up 1. And 9, 2 goes way over 9 up 2. So we still get the same shape as what we saw before, But now it's kind of different. It's inverted because it's an inverse function. And now it's swooping in a different direction than it was before. Also, you're probably going to realize that some things are backwards. So now our asymptote line is actually this vertical line here, rather than the horizontal one. We don't care about crossing it. That's fine, but we can't cross the vertical line now. What happened was, just like our x and y values got switched around, the domain and the range are now switched around. So in this case, our graph would continue down and up forever. So we can write this as y being an element of the real numbers, or y going from negative infinity to infinity forever and ever. But the domain is restricted because now we're stuck at this line. We can't go past this line, which is the line x equal to 0. So we need everything to be greater than 0 in this case. And then I already kind of hinted at what the equation is. It's x equals 0 because all of the lines on this asymptote line are 0 for the x value. Okay, so just take a minute, kind of absorb that, recognize that these are the opposite from what they were before. That's the major difference. But so are the table values. So everything's just inverted. All right, let's try a few more of these. Here we have log base 4 of x minus 3 plus 1. So we want to think of our shift point. That's what I'm going to do right away. The shift point here would be positive 3, positive 1, because this is our h, this is our k. H is the opposite, k stays the same. So 3, 1 is over 3, up 1, this point right here. So I'm going to draw my dashed lines going through that. Okay. And now we need to know what numbers to be using. So we have to rewrite it in the exponential form so we know how we want to get our table values. What we're going to do is we're going to ignore these points right here. We are only going to treat it like we're looking at the equation y equals log base 4 of x. We've already accounted for the shift part, so now let's just rewrite this. So I would take the 4, swing it under the y. This would become 4 to the y equals x. Now we graph it. So you only ever need 2 columns for this one, which is nice. You just have to remember that your numbers are going to go -2, -1, 0, 1, and 2 in the y column. Now it's the x column we need to do a little bit more thinking of. So if I were to take 4 to the -2 power, I end up with 1/16, because you flip it, square the 4. Then I would get 1/4, 1, 4, and 16. Okay, now I'm going to graph these and we can think about that. Remember, these are your x values, so now you're moving just slightly to the right, and then these ones are going down. So I'm going slightly to the right, down 2. So this point right here. Let me change my color, just so we can see that a little better. And then slightly to the right, 1/4, down 1, so like right there. And then we got 1, 0, because I'm counting from this new shift point. And then 4, 1, 1, 2, 3, 4, up 1. And 16, 2 would go way off to the right, so we just know that it has to go somewhere over there. So connect your points. Remember, this is going 2 directions. It's going up and down forever rather than left and right. So our domain we can write as x greater than, and hopefully we picked up on this, but it's actually the h value. I should have mentioned that before. That's the x value, which is our asymptote. That's this line right here. X has to be greater than that because everything is to the right of it, so it gets bigger. Our asymptote line, if you want to fill that in, is x equals 3. That's the asymptote, the dashed line going up and down here. And then the range is the nice part. We can write that as y being an element of the real numbers, or we can write that as y can go from -infinity to +infinity. Also, I should write the domain option for that. I do apologize. Let me throw that in here. So that would be from 3 to infinity. I'm going to go back up and throw that on this one too. And that would be from 0 to infinity for the x. That's the set notation form. Okay, but we're kind of cruising through these. Let's go ahead and look at a couple more of them. And then this one is just a review of the old parts. Okay, so this one we would write as our shift is -1, 0. This is our H. The K value would be like out here as a +0. So this one just goes left 1. So we just need to make sure to count left 1. I'm just going to put this here. The 0 part would mean that we're still looking at the y-axis. So this is our point that we're graphing from. It's not an actual point. Then when we look at this, we're trying to find it for the inverse of y equals the log of 2x. We already accounted for the 1. So when I rewrite it, I swing the 2 under the y, set it equal to x, and now I know what I'm filling in for my table. Remember to start with your y column, -2, -1, 0, 1, and 2. Your x column is going to be 2 to the -2, and that's going to give us 1/4. A lot of these values we've seen repeated, so hopefully you kind of remember the patterns, but 1/4, 1/2, 1, 2, and 4. Now let's go ahead and graph it. So 1/4 is going to go over 1/4, down 2, about right here. Over 1/2, down 1 is right there. 1, 0, 2, 1, and 4, 2 is right here. We just connect those. Make sure that you're not going to cross your x asymptote here. This horizontal line right there, or vertical line, excuse me. And then our domain for this, we need x to be greater than -1. That's the h value. Or if you want to write that in set notation, from -1 to infinity. The range part is going to be y is an element of the real numbers, which means y extends from -infinity to +infinity, going up and down forever and ever. And then the asymptote line is x equals -1. So once you've practiced a few of these, they do go pretty quickly. This last one is one of the old types of functions that we used to do. But for the sake of this video, I'm just worried that my iPad's going to cut out, so I don't want to lose this video. So I'm going to end it here. If you need to look back at how to graph these, go back to the very first section. And that's it for this one.